Okay, Year 11, we're going to go through the separates paper bit by bit. Hopefully you will be able to take a different coloured pen and annotate your own paper and see where you've missed out on marks. And I would suggest you maybe have another piece of paper where you can write down key points that you need to look up if you are still struggling with those sections. Clearly, when you've been through and looked at where your low marks are, you'll have a clearer idea of the topics that are a main focus for you as an individual. Okay, so starting at the very first question, it's talking about structure and bonding, and it's talking about intermolecular forces between particles. So first of all, intermolecular, if it's between molecules, intermolecular, then you must be looking at simple covalent bonding. Okay, diamond is giant covalent, magnesium is metallic, and sodium chloride is giant ionic, so it can't be any of those. Looking at polythene, it's made up of small molecules linked together by those red dotted lines, which are the intermolecular forces, and water, even smaller molecules, are H2O with the intermolecular forces between those molecules. So clearly our answers to our question are polythene and water. Second part then, it's asking you for a long answer question, so you need to review and think about what you know. Carbon dioxide, okay, is made up of molecules, small molecules, whereas both magnesium oxide and silicon dioxide are giant structures. So small molecules, our black lines are covalent bonds. Why are there two there? Because we have a double bond, two shared pairs of electrons between our carbons and our oxygens, with weak intermolecular forces. Magnesium oxide, metal, non-metal, therefore giant ionic. Regular 3D structure between positive and negative ions, therefore electrostatic attraction. And finally, silicon dioxide, remember the one that looks like diamond, giant covalent bonds within our giant structure. 4 covalent bonds for every silicon and 2 covalent bonds for every oxygen. So not quite as strong as our diamond structure, but sand, silicon dioxide, still a giant bond structure. Okay, so compare the structure and bonding of these 3 compounds. In order to get your 6 marks, you've got to think about not just what the structures are, but compare them. One is stronger than the other. One has electrostatic forces because it has charged particles, the other. So you've got to make sure you put in this but that, compare this with that. This has this, whereas this has something different. Okay, so our key points need to be simple molecular structures for carbon dioxide, covalent bonds within a small molecule, weak intermolecular forces. Magnesium oxide, giant ionic structure between a metal and a non-metal, looking at oppositely charged positive and negative ions, and therefore strong ionic bonds with electrostatic forces holding them together. Silicon dioxide, giant covalent, shared pairs of electrons, strong covalent bonds within our giant structure. Okay. Now notice it talks about comparing the structure and the bonding. It does not talk about linking that to the properties. So you're not talking about high melting points, boiling points, anything else which is the properties of our compound, which is where a lot of you went wrong. Moving on to question 2 then. Metals and the reactivity series. Transition metals, remember that central block. We're looking at things like copper and lead and nickel and gold and silver. Okay, so metals would have these sort of properties: good conductors, hard, strong, high densities, high melting points. Transition metals in particular are the ones that form coloured compounds and are malleable, ductile, etc. So looking at our substances here, soft metals are the alkali metals. Colourless compounds, not normally, but can do. Different charges, yes, they do form different charges. High melting points, true of all metals, definitely. Low densities, ones that float on water, is our alkali metals again. Okay, so transition metals often form coloured compounds, though not always, and importantly, they're used as catalysts, worth remembering. Second part, and I think question 2 is quite a difficult question. There's a lot of information they ask you to pass on in the longer style answer, so there's a lot of planning needed here. Add copper metal to colour silver nitrate. Copper is more reactive than silver, therefore we're looking at a displacement process. How does that happen? What does it show? We see pale grey crystals forming, while copper metal was our orangey metal, and grey crystals will be our silver. Solution turning blue because a copper compound is being formed. So, in order to get your 3 marks, copper metals displace the silver ions from the solution, the copper is oxidized, silver is reduced, silver atoms were formed, and the solution turns blue because copper ions or copper nitrate solution was formed. So that's why you see your colour change. Notice explain, not state. So again, you're explaining why you see those grey crystals forming as the silver forms, and why the solution turns blue as the copper compound, copper nitrate, particularly is formed. Okay. Part 3, again a longer answer, so we're looking for planning your investigation, thinking about the steps that allow you to identify those metals, magnesium, iron and copper, and make sure that you explain the result, what the results are going to be. So we could be looking at a reaction between the metals and the acid, therefore we're looking at the formation of salt. You won't see the metal salt because it's dissolved in water, and hydrogen gas being given off. So our independent variable is by changing the metal. Our dependent variable is looking at how quickly that gas is produced. What do we need to keep the same? We need to keep the same the amount of metal, the way in which the metal is ground down, so is it in large lumps, is it in fine powder, the concentration and volume of the acid, don't just say amount, and the temperature at which the reaction is taking place. So set volume of set concentration to our test tube so that we know how much acid we've exactly got. Add exactly the same amount of metal to each one, and then you can either compare the amount of fizzing or measure the volume of gas being given off in a fixed time. Alternatively, you could look at the temperature change in a fixed time, and therefore give the order of our metals. So the most reactive being the one that gives off the most gas in that time or gives off the gas most quickly. Alternatively, the one that shows the largest temperature change. Part 4, isotopes. Different forms of the same element, the same atom, with different numbers of electrons and hence different masses. So we're looking at percentage, working out our percentages, and from that working out our overall average mass. In the case of our metal, so you've got a definition here for chlorine. Okay, in terms of our metal here, we've got 30%, which is 0.3 of our total, is element with mass number 203, and 70%, 0.7, has mass number 205. To calculate the overall or average mass, therefore, 0.3 of it will be 203, 0.7 of it will be 205. Add those two together and you will get 204.4. You could equally well do 30 times 203 and 70 times 205 to work out the mass of 100 atoms and divide your final answer by 100 to get 204.4. As long as you've shown it clearly and got the right answer, then you will get your 2 marks. Okay, question 3, we're now looking at a reaction between silver nitrate and sodium iodide solutions. This is a double decomposition or formation of a precipitate. You can see because the silver iodide is being formed as a solid on our product side. So they are simply starting off with their chemical and adding the second substance and measuring the masses each time. Since we're trying to talk about, explain how the results demonstrate the law of conservation of mass and use the data, we need to think about what changes are happening. So very simply, we want to look at the mass at the start, big A and big B, the mass at the end, big A and big B. Notice that those two total masses are the same, hence we haven't lost or gained any substances, and that is our definition of our law of conservation of mass. Part 2 suggests how the student could separate the insoluble silver iodide, the thing which is a solid. So a solid from a solution, we simply need to filter it. We then want to purify the separated silver iodide, so they rinse it, getting rid of any of the substances which were on the surface of it. Then warm that silver iodide solution. So what's going to be removed when they rinse it? Any of those solutions, any of the dissolved substances, in particular the second product. Why do we warm the silver iodide? To evaporate off the water, to concentrate our solution, and then to dry the final silver iodide sample. Calculate the atom economy for the production of silver iodide. What does atom economy mean? Okay, our atom economy is comparing the amount of waste with the amount of useful substance. So in this case, with our formation of carbon dioxide, that was our waste, and the hydrogen was what they were trying to make. So we need to know how much is the product compared to what we started off with. So the mass of the desired substance compared with the mass of what we started off with in total, and then converting it into a percentage. So looking at our substance here, we wanted to make silver iodide, and the silver iodide has a mass of 235. We started off with silver nitrate and potassium and sodium iodide, 170 plus 150, and therefore our final answer 73.4375 to three significant figures. 73.4, we don't round up because the 3 below that is less than 5, so 73.4 to three significant figures. And finally, why is it a good idea to have high atom economy in terms of our industrial processes? Well, we've got to think about making best use of our raw materials, and producing less waste, so more efficient use of our resources. So we produce less waste. We've got to link any concept of cost. I've said to you before, don't talk about cost unless you quantify it, link it to something, so link it to the raw materials or the waste products of our substance. Okay, question 4, electrolysis. This is a lovely practical where we start off with copper chromate in solution, and it's green because it has two coloured compounds in there which are mixed together to give that view of green. So copper chromate is blue, the copper is blue and the chromate is yellow. Put the two together and you see green. We switch on the power, and obviously we're then going to see our positive ions moving towards the negative side and our negative ions moving towards the positive side. Hence we see the separation of the yellow moving towards the positive side and the blue moving towards the negative side, because that's where they're attracted. Okay. So if we're explaining the colour change at the positive side, what do we see at the positive side? We see a yellow colour formed, because that's where our chromate ions are attracted towards. Gas produced at the positive electrode was oxygen. Oxygen was produced from hydroxide ions. Name the substance in the solution that provided the hydroxide ions. That's our water. Sorry, the R seems to have moved. Remember, if we're looking at electrolysis of solutions, then when we have metals which are too reactive, or we have sulfate ions, etc., we see the water, ionized water, taking part in the electrolysis process. So these are our key facts we need to remember. If we're thinking about at the anode, we'll see our halides, chloride, bromide, iodide being produced. But if we have carbonate, nitrate or sulfate in our solution, then we won't. We'll see water, we'll see oxygen coming from the hydroxide from the water. We don't ever see carbonate, nitrate or sulfate being produced. They stay in the solution. Equally, remember, if we're talking about the cathode side where our metals are produced, low reactivity metals will be displaced. anything above hydrogen, the reactivity series will not be displaced, and instead we'll see hydrogen coming from the water. So you'll see copper, silver, gold, for example, being discharged, or you'll see hydrogen being discharged. You won't see our more reactive metals, they stay in solution. Okay, oxidation is loss, reduction is gain, so what's happening at our electrodes? We see our negative ions losing electrons and turning back into our element, and those electrons flow through the circuit. Those electrons are then given to our positive ions, which convert into our metal or into our hydrogen. So we see oxidation at the anode, where we are loss of electrons, and reduction at the cathode, where there's gain of electrons. How does the solid form at the negative electrode then? Well, there's our process. We start off with copper ions attracted towards the cathode, where they gain electrons, they are reduced, and they deposit copper metal on the surface of the electrode, so the copper plating process. You need to have those 3 steps to get your 3 separate marks. The student repeated the investigation using potassium iodide instead of copper chromate. Name the product at each side. Now remember, it's still a solution. Think back to those rules we've done. At the negative side, we'll see our positive ions. Because it's potassium, potassium is too reactive, more reactive than hydrogen, so we would see hydrogen being produced. And at our positive side, we'd see our negative ions being attracted, in this case the iodide. Halides are low in reactivity, they are displaced, therefore we would see hydrogen at the negative, and we would see iodine at the negative. We spent quite a lot of time talking about the different atomic models. You've done a home learning on this if you go back into year 9, but you can just simply revise it. We're talking about the development of those scientific theories, so the idea about electrons being discovered, then the concept of our plum pudding model, then our famous gold foil scattering experiment in Rutherford, then the development of the Bohr model, after that the discovery of protons, and after that the discovery of neutrons. So make sure you don't refer to protons or neutrons too early in the process. If you like pictures, there you go with your pictures. So that would be what I would suggest you bring to mind as soon as you read the beginning of the question. Think about the differences between the plum pudding model and our nuclear model. So we have our electrons, we know about our electrons, and hence the plum pudding model existed. Those electrons were just embedded in that Christmas pudding model, whereas in our nuclear model we had the electrons orbiting. Positive charge was diverse and spread out, diffuse and spread out in our plum pudding model, localized in the nucleus by the time we get to our nuclear model. No empty space, mostly empty space but a small nucleus. In plum pudding model, no idea about the nucleus, which obviously then was emerging with our work with Rutherford. So, plum pudding model did not have a nucleus. 3 other differences between the nuclear model and the plum pudding model. Okay, so in our plum pudding model, we had our negative charge spread throughout the structure, whereas the nuclear model had the electrons in particular orbits, particular moving locations. Plum pudding model has no empty space, whereas the nuclear model is mostly empty space. In our nuclear model, we have the positive charge centered in the nucleus in the center, whereas it was spread out throughout the whole structure. Okay, remembering our gold foil experiment, most of the alpha particle spread goes straight through because most of it is empty, the atom is empty space. The positive alpha particles are very occasionally bounced back, so they must have hit something which was dense, which also had a positive charge, and a few of them are displaced or just deflected from their path by that. Okay. So Bohr then adapted our nuclear model. What did he do to change it? As far as Bohr was concerned, we ended up producing our electron shells, or our energy levels. So he's talked about working out where the electrons were found, putting them into specific energy levels around the surface of the outside part of the atom. Okay, and each of those shells is limited in terms of the number of electrons it can contain. Mendeleev published his periodic table in 1869. He arranged the orders in terms of atomic weight. Remember atomic weight. And then he reversed some of those pairs of elements. The student suggested Mendeleev's reasoning for reversing the order was to arrange the elements in order of atomic number. Why is that not right? Because at that point, atomic number, remember, is number of protons, and they had no idea that protons existed. Okay, so atomic number links to protons. Protons had not yet been discovered, therefore there could not have been any link between those two. And I've heard many pupils, students, refer to that, so make sure you're not one of them. Why did he actually reverse the order? So he's acknowledging that their atomic weights were in one order, but he pops them into a different order so that he had elements with similar properties in similar vertical columns or areas of the table. Okay, so he ordered them so that their chemicals with similar properties were grouped together. Question 6, displacement reactions. What is activation energy? Think about our energy level diagrams. The activation energy is the energy that is taken in by our reactants to allow a reaction to start. Okay, so it's the energy taken in to allow a reaction to start, usually associated with breaking bonds. First bit of quantitative work now, looking at calculations. So notice we have a balanced equation, and we have 1 kilogram of aluminium and 3 kilograms of iron oxide. In order to show the limiting reactants, we've got to convert from masses into moles and use our mole ratio. Okay, so there are different ways of doing this, but first of all, get your units right. So think about 1,000 grams of aluminium, 3,000 grams of iron oxide. Then convert from masses into moles. So we divide 1,000 by 27 and we divide 3,000 by 160 to give us the number of moles present. Now, according to our equation, our mole ratio should be 2 to 1. It states it in the question. So if we had 37 moles of aluminium, how many moles of iron oxide would we need to react with it? Notice 18.5, half as much, and we've actually got 18.75. So all of our aluminium can react with 18.5, so there's 0.25 of iron oxide in excess. Hence, we should be able to say that the aluminium is our limiting reactant because there is excess iron oxide left over, that small amount left over at the end. Breakdown of the marks to get your 4. Magnesium displaces zinc from zinc sulfate solution. Complete the ionic equation. We're only talking about the ions present. Okay, so magnesium as a metal converts into magnesium ions. The 2 electrons from our magnesium are then given to the zinc ions to produce zinc metal. Okay, so we are producing zinc solid. It tells you to include the state symbols, so you need to make sure you've done so. Explain why the reaction between magnesium atoms and zinc ions is both oxidation and reduction. So let's think about them in 2 halves. So the magnesium is losing 2 electrons, therefore it's being oxidized. The zinc is gaining 2 electrons and therefore it's being reduced. You can think about our 2 separate half equations in terms of loss and gain of electrons. So magnesium is oxidized because it lost electrons, zinc is reduced because it gains electrons.